How do you know if an atom is stable? In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. For more information on atomic structure, watch this video. A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus, and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today, but not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus. Alpha decay is the loss of an alpha particle. An alpha particle is made of two neutrons and two protons. They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta minus decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron. Positrons have the same mass as electrons, but the opposite charge. By losing a proton but gaining a neutron means the mass number stays the same, but the loss of a proton means the atomic number decreases by 1. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta minus decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta plus decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay. In this video, we have learned that unstable nuclei either have too many protons or too many neutrons, which upsets the strong nuclear force holding the atom together. Unstable nuclei try to balance themselves by giving off the excess proton or neutron either through alpha, beta minus, or beta plus decay. At the start of the 20th century, scientists had a good estimate of how old the Earth was, at least several billion years of age. This led to the tricky question as to how the Sun not only generated heat and light, but how it had done this for so long. Theories based on known science made no sense. It was impossible that the conventional chemical combustion of a fuel could be sustained for so long, and other ideas of gravitational shrinkage ran into similar time constraints. In 1926, just after it was found that the Sun was only made mainly of hydrogen and helium, Eddington proposed that nuclear fusion might explain the enormous energy output and longevity of a star. It was Hans Bethe in 1939 who proposed a route of making helium from hydrogen, elements that were known to be dominant in the Sun. Fusion is the joining together of light atomic nuclei to produce a heavier one. It may sound simple, but the conditions needed to bring together positively charged nuclei and overcome mutual repulsion are extreme, to say the least. Consider the simple example of fusing deuterium to make helium. When two deuterium nuclei fuse to make one helium nucleus, there is a small but measurable loss in mass, about 0.5%. We need Einstein and his famous equation, E equals mc squared. This equation links mass with energy. They are the same thing. E equals energy measured in joules, m mass in kilograms, and c speed of light, which is 3 × 10 to the power of 8 meters per second. If 1 mole of helium is made, which is 4 grams, then using E equals mc squared, the energy released is about 23 × 10 to the power of 8 kilojoules. That's a lot of energy. This equates to about 72,000 litres of petrol, enough to fill up 1,440 family cars, or, when burned in oxygen, could last one car for a 720,000 mile journey, or 1,160,000 kilometers, a trip that would take you around the world almost 29 times. This, of course, ignores the extreme conditions of high temperature and pressure to bring about fusion, the conditions for which as yet only exist at the core of a star and for an instant when a thermonuclear or hydrogen bomb is detonated. In a hydrogen bomb, a conventional fission bomb is used to heat up and compress a small amount of deuterium and tritium so as to initiate fusion to produce helium. Scientists have been trying to control the fusion reaction for over 60 years, so it can be used to generate clean energy. The major issue is getting enough nuclei close together and for long enough for fusion to take place. The International Thermonuclear Experimental Reactor, or ITER, is one of many types being built today. It will use deuterium and tritium as fuel in this fusion reaction. Consider this: a 1,000 megawatt coal-fired power plant requires 2.7 million tons of coal per year, whereas ITER would only require 250 kilos of fuel per year, half of it deuterium and half tritium. While deuterium can be sourced from seawater, tritium, due to its short half-life and rarity, must be made via neutron bombardment of lithium, an element which seawater also contains in large amounts. This explains why we have tried for decades to recreate the Sun here on Earth, but it always seems that success is just around the corner. Well, maybe next year. Very often in science, you make a discovery that you were not looking for. In 1934, Enrico Fermi was bombarding the large nucleus of uranium with the recently discovered subatomic particle called the neutron. He knew that the uranium sample had changed in some way, but couldn't determine how. He had wanted to see if moderated neutrons would pass through the nucleus. In 1938, this work was repeated by Otto Hahn and Lise Meitner. So Hahn and Meitner had discovered that a captured neutron causes fission, a word they borrowed from cell biology, which described the process when cells split apart. They predicted that a chain reaction was possible as new neutrons caused more fission, which raised the possibility of a new source of energy.
Upon fission of a single nucleus of uranium, you can see we get both barium and krypton, also called daughter nuclides, along with 3 neutrons.
An atom of uranium will rarely undergo fission without first capturing a neutron. Then where does the energy that Hahn and Mittner referred to come from? Let's look at the mass change during fission. There is a very small mass loss on fission of the nucleus. So where has this mass gone? Here we need to look at the work of Einstein. E equals mc squared. This must be the world's most famous equation and links mass with energy, where E is energy measured in joules, m is mass measured in kilograms, and c is speed of light, which is 3 × 10⁸ meters per second. On fission, about 0.1% mass loss is observed. So if 1 kilogram of uranium-235 underwent fission, the energy transfer would be E equals 0.001 kilograms times 3 × 10⁸ squared, which equals 9 × 10⁻13 joules. To get this amount of energy from burning coal, you would need to burn 2,000 tons. That's 1,000,000 times the mass of the uranium. On fission and subsequent chain reaction, a lot of energy, including gamma rays, will be released. For a chain reaction to be self-sustaining, there needs to be a minimum amount of material present. This is known as the critical mass. Below this critical mass, too many neutrons are lost from the metal surface and so take no part in the chain reaction. The discovery of nuclear fission was only the beginning of the nuclear age. It was Enrico Fermi who built the world's first nuclear reactor, named Chicago Pile 1, which went critical in late 1942, showing that a controlled chain reaction was possible. The Manhattan Project then led to the rapid development of fission bombs based on uranium and plutonium in 1945. In a fission bomb, 2 subcritical masses of uranium or plutonium are quickly pushed together using conventional high explosives, which results in an uncontrolled chain reaction with an almost instant release of huge amounts of energy as heat, light, and gamma rays. In a nuclear reactor, the controlled slow release of energy is used to heat up a closed loop of coolant, which passes to heat exchangers, which then boil water to provide steam to turn electrical generators. The output of the reactor is altered by raising or lowering the control rods in the core. These rods absorb neutrons and so determine how much fission is taking place.